Venkat and host Jay.
Okay, Anna.
Okay, good evening. Good evening. Can you hear me? Good evening. Can you hear me? Thank you. So let's get started. Yesterday, we have seen two ways of solving diode problems. We know that a diode is forward biased only when the current flowing through the diode is positive. So we replace a diode with short circuit or 0.7 volts and we calculated the current. And then if the current is positive, the diode is forward biased. But for single diode problems, what we did is we either found the current or we individually calculated VA and VC, anode voltage and cathode voltage separately. And then if anode is more positive than cathode, if anode is voltage is greater than cathode, we said that the diode is forward bias, right? But if it fails, then we have to replace the diode by open switch and calculate the voltage across the diode. And if the voltage across the diode happens to be negative, then the diode is reverse bias, right? Negative or less than 0.7 volts. So this is something we've been doing, right? Now, I think we've, yesterday we stopped at a problem where I asked you to track the direction of current, right? So when you move from the source to the destination, you should always see that the current always travels from anode to cathode, is it not? So on the same token, if I give you if I ask you find ID1, ID2, ID3, and ID4. So how do you travel? Because you have to travel from anode to cathode, right? So how does the current travel? Or for the same circuit, let me change the direction of current. Find ID1, ID2, ID3, and ID4. So same problems, but the direction of current has changed. So how will you travel? You have to start from, say, point A, from this point A, and then you have to come back to the same point, right? So you have to start from here and you have to come back to the same point. So similarly, you should start from this point A and then come back to the same point. So here you have to travel in the clockwise direction, but this problem, you have to go in the anti-clockwise. So how do you go from that node and then back to the same node? Very good. So most of you have answered correctly. Okay, so tell me, suppose the current direction is in this fashion. So I have to come back to the same point. So how do I travel? Can I go through D1? Can I go through D1? No, is it not? So why I can't go through D1? Because the terminal is not anode, but it is cathode, right? So it have to move because I have two paths for it. I have two paths for it. I can't go through D1, so I have to go through D2. But when I reach this node here, when I reach this node, again I have two paths for it to travel. Then how do I travel? Can I go through D4? So D1 is ruled out. So the current cannot pass through D1. So D1 is left over. Now through D2, but again you have two paths for it to flow. Can you go through D4? No, because the terminal is cathode, right? So current cannot flow from cathode to anode, but it flows from anode to cathode. So D4 it cannot travel. So it has to travel through R. And now, because D1 is ruled out, can it go through D3? Yeah, because this is anode. And now, because it cannot go through D4, so this is the path. So let me draw it in this fashion. So this is I. It goes like this, and then the resistor like this, and then reach here, right? So this is D2 and D3. So what you said is correct. ID2 equal to ID3 equal to I. ID2 equal to ID3 equal to I, right? But ID1 equal to ID4 equal to 0, right? So no current flows through D1 and D4. The current has to flow from D2. So it's going to flow in this fashion, right? So current always needs a closed path, a closed path for it to flow, right? Very good. Well, so that means now in this present problem, then how do you start? This current I, right? When the current reaches this node here, it has two paths for it to travel. Which path will it choose? Will it choose D3 or, and then it reaches this node. When it reaches this node, will it choose D2 or R? Will it choose D2 or R? It cannot choose D2 because current cannot flow from cathode to anode. It has to flow from anode to cathode. So it will travel like this and then choose D1. So let me draw it in this fashion. This is D4, R, D1, right? So ID4 equal to ID1 equal to I. So what is ID2 and ID3? ID2 equal to ID3 equal to 0. So current always needs a closed path for it to travel, right? It needs a closed path. say your Vn is Vm sine t, right? What will be your V naught? Find V naught. Find V naught, or you can say sketch V naught. Sketch V naught. Very good. So this is a very popular circuit, right? So what is the name of this circuit? You all know this is called the bridge rectifier. Very good, bridge rectifier. It's popularly called as the bridge rectifier. So during positive cycle, the current direction is in this fashion, right? During the positive cycle, the current direction is in this fashion. During the negative cycle, the current direction is in the opposite. So when the current has to travel in this direction, which path will it flow? This is for positive cycle. And right. So during positive cycle, the current has to reach, it cannot go through D2, it has to go through D1, resistor and D3, right? D1 is on and D3 is on. During the positive cycle, D1 is on and D3 is on. Now this is the direction of current. So the current is flowing from anode to cathode through D1 and anode to cathode through D3, right? So the V naught here, you can see the direction of current and the polarities here of V naught, both are same, right? So you get a positive output here. But what happens during negative cycle? During negative cycle, the current direction has changed, right? The current direction, you can, if you want, you can reverse the polarity, or if you don't want to reverse the polarity, fine, at least reverse the direction of current, right? So let it be Vm sine omega t. Now we have reversed the direction of current. When you reverse the direction of current, how will the current travel now in the negative cycle? So the current has to choose D4 and D2. D4 and D2, right? Now you can see that the current direction hasn't changed, right? Either in positive cycle or in negative cycle. So this is Vin, and here you have the resistor. You're taking the output here, right? You're taking the output. Is exactly V, right? This is in positive cycle. V naught is exactly V. But what is happening in negative cycle? In negative cycle, the current direction at the input has changed. But it's as if the first case, because in the first case, you can see that the current is flowing from, suppose this is node A, this is B. The current is flowing from A to B. And in the negative cycle, also the current is flowing from A to B. What do you mean by this? What do you mean by this? You can see here, suppose I have an input voltage V in. I have an input voltage V in. And suppose I have a network like this. A network like this. If both resistors are of same value, right? What is your V naught? What is your V naught? V naught is going to be V in by 2. V naught is going to be V in by 2, but that is too fast. Instead, what I can say is, I will take this as node A and node B. During positive cycle, this is the direction of current. So the current will travel from A to B, no problem. So when you sketch the output, suppose you are given a 5 volt waveform here, 5 volts, you're going to get a positive cycle, 2.5 volt. But what happens in the negative cycle? In the negative cycle, when the current changes, the direction, when in the negative cycle, now the current does not flow from A to B, it flows from B to A. It flows from B to A. So if you give a negative voltage, you're going to get a negative output here. So for positive cycle, because if you connect a multi from the plus terminal to the negative, suppose if this is the what you call the black wire, the red one here, there's a red one, and there's a black one in the multimeter. So if the current is flowing from the red to black, right, higher potential to lower, you get positive, but if the negative. But in a bridge rectifier, what happened is the current to black, red to black. Irrespective of any variation in input during positive cycle, if you give V in positive, your V naught, the current is flowing from A to B in positive cycle, so you get positive. But in negative cycle, the current direction has changed here. It has changed, but at the output, the current direction still remains same. So A to B. So you will always find a positive waveform going here, right? So it's understood that in this duration, your V naught is V in, but in this duration, you will change V in. The current direction at the input has changed, but the load is not experiencing that change. But can you see in a voltage divider, simple voltage divider, when the current direction at the input changes, the load resistor here R is also experiencing that change. First from A to B and then B to A and A to B and B to A, positive, negative, positive, negative. But here, what is happening? A to B, 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 A to B. So the output is always going to be unidirectional. It's always going to be unidirectional in a bridge rectifier, right? So the current direction has not changed in a bridge rectifier because it's a very clever way of connecting the diodes. They connected the diodes in such a fashion that the current will always travel from where to where? A to B, A to B, right? First, the D1 gets on. The first node that is encountered is A. See, during positive cycle, D1 getting on is not a big thing. D2 should be off. That is more important. D2 should be off so that you don't reach B first. You should always reach A first so that you get A to B, A to B, A to B unidirectional. So because you have to reach A first, the D is in the opposite. So but the moment the D1 gets on, the current will first go to node A, and then after that, it has to reach B through the resistor. Similarly, in the negative cycle, what is happening? D4 is getting on. D4 is getting on is not a big thing. D3 should be off. In negative cycle, D3 should be off. So the diode is very cleverly put in the opposite. So the first, once D4 gets on, the current will again choose first node A. After reaching node A, through the resistor, it will reach B, right? So at any cycle, you have to reach first node A. So it's something like here, though you change it, the current should always flow in the same direction. But can it happen in a simple voltage divider? Can it happen in a simple volt? You have an can it happen that during positive cycle in this direction, during negative cycle also in the same direction, again positive cycle, negative cycle, the same direction? Can you have? No. When the signal changes, the direction changes at the load also. So this is not rectification. For rectification, you should have a clever way of connecting these diodes, right? Because the diode, the bridge rectifier, very good. So this is popularly called the bridge rectifier. And what about the reverse bias diode? In the positive cycle, what about the reverse bias diode? How much voltage is there across the reverse bias diode? That is called the PIV. PIV. What is PIV? It is the maximum voltage across a diode in reverse bias. It is the maximum voltage across a diode in reverse bias, right? It is the maximum voltage across a diode in reverse bias. PIV stands for peak inverse voltage. PIV stands for peak inverse voltage. It is a maximum voltage across a diode in what bias? Reverse bias, right? So during positive cycle, we have seen here, during positive cycle, which diode is on? This diode here. Now here we have a diode. Here we have a diode, right? If you apply KVL here, minus VPIV, because this is a diode in reverse bias, plus V naught equal to 0. VPIV equal to V naught or V naught max. What is the maximum value of V naught? The maximum value of Vm sine omega t is Vm. It is going to be Vm, right? The peak of the input is a maximum voltage that it appears across the diode. The peak inverse voltage. So similarly, so if this is your V naught, or this is your V naught, or this is your V naught. What are these waveforms like, right? This is, of course, a sine wave. The sine wave. This is the output of a half wave rectifier. This is an output of a full wave rectifier. Full wave rectifier. Now, how do you calculate the average value or the RMS value? RMS. So you, or for a sine wave, we know that the average value is always going to be 0. And what is RMS? RMS is the root mean square, right? So you're going to get Vm by root 2. So if you square the negative cycle, you're going to get positive. So even for a full wave rectified output, you're going to get Vm by root 2. Now, what about average value? Average value of a half wave rectifier. Average. It is area by the base, isn't it? So what will you get if you have 1 by 2 pi, 0 to pi for a half wave rectifier? Have Vm sine omega t dt or sine t dt. Now, what is integration of sine? It's minus cos. So cos 0, 1, cos pi minus 1. 1 minus of minus 1 is 2. 2 gets cancelled. Vm by pi, half wave rectifier output, Vm by pi. And for the same 2 pi duration, if you have one more, Vm by pi plus Vm by pi, you're going to have 2 Vm by pi. What about half wave rectifier RMS value? It is Vm by 2. Right? So what is RMS? RMS is the root mean square. So you can calculate the RMS value also for all these waveforms, right? You get sine square and you know how to solve sine square with the help of cos 2 theta, right? Now, they're saying VPIV should be reversed in polarity, right? Somebody asking because the diode is in this fashion, right? The diode is in this fashion. Remember, no device has polarities. Please, I'm going to make a statement you should all remember now. This statement for a lifetime, you have to remember, right? No device has polarities. Capacitor, no polarities. Diode, no polarities. Zener, no polarities. MOSFET, no polarities. No device has polarities. Polarities will come only with the direction of current. Remember, I repeat, no device has polarities. Polarities will come only with the direction of current. Are you getting? Right? So keep that in mind. Now, this end is plus, that end is minus. So VPIV, if you reverse the polarity, you might get minus, right? So let me give you an example for that. Example, no device has polarities. polarities should be given only with the direction of current. But if the examiner has given polarities in his own way, don't change it. Probably you might get a negative answer. So it doesn't mean. But when you are giving polarities, should always give with the direction of current. How? Example. Let me give you an example, right? Suppose I'm having a voltage here like this, plus minus. It's customary that we know that the current will always travel from plus and then reach to minus. So this is the direction. Here I'm having a capacitor, a Zener like this, a Zener like this, a diode like this, right? Now, what polarities will you take? So current will flow from plus to minus in this direction. So because it goes in this direction, what we have to do is you should blindly take plus minus, plus minus, plus minus, plus minus like this. Polarities will always get with the direction. You can call it V cap here because it's a capacitor. You can call it VZ. You can call it V Zener forward. You can call it VD on, your wish, right? But the polarities will come only with the direction of current. Suppose I have a voltage like this. This is plus minus. And here you have the same capacitor and a Zener and a diode like this. So what will you do now? So you have to take in this direction. So you have to take plus minus, plus minus, plus minus, plus minus. No device has polarities. The polarities will come only with the direction of flow of current, right? Think about it. It's a good doubt, right? The student asked in the comment section, he said, what about a diode? How will you take plus minus, right? We should not take, by the direction of flow of current, you can always take plus minus, right? But if the examiner has given, in his own fashion, so don't worry about it, right? But when you take the current direction, this is the way you should take, right? But the good news is you will realize that in Zener, especially in Zener, if the current goes from anode to cathode, you will have a chota voltage. For example, here you'll have a chota voltage in Zener, 0.7, but anode to cathode, right? So 0.7. But when it goes from cathode to anode, here you will call it VZ. You'll call it 0.7. Chota voltage in forward bias, bada voltage in reverse bias, right? But the polarities are, the polarities will always come only from the direction of flow of current, right? Especially capacitors you have done. If you have a capacitor like this, and there is a flow of current here, what will you do? You should take plus here and minus here. And then the capacitor will allow you to use a formula Vc equal to 1 by C integral IDT. But if somebody has already taken, if the current is flowing in this direction, then what you should take? This is a current. This is plus minus. Then your Vc is again 1 by C integral IDT. Sometimes in problems, the examiner takes a polarity like this, plus minus, and you have assumed a direction like this. Then what will you do? This is your current, your assumption, but the examiner has. Then while writing a formula, you have to be very careful. Minus Vc is 1 by C integral IDT. Are you getting it? Right? But when you are taking polarities, this is given by the examiner, the third case. But the first two cases which I've drawn here, if you are taking, please take polarities based on the direction of flow of current. The current always flows from higher potential to lower potential, right? Find V naught average. This is a gate problem. Find V naught average. Okay, so have you understood? When you're taking polarities, you should always take in this fashion. Are you getting right? Now, suppose here, if the examiner has already given a polarity, what will you do? If the examiner has already given a polarity, suppose here there is a diode here, and he calls this as VD, and this is your VPIV. Now, what is the relationship between VD and VPIV? VD is going to be minus of VPIV. VD is going to be minus of VPIV, and your PIV is already how much? VM, right? So when somebody says what is VPIV, the voltage across a diode, that is nothing but VM. But intentionally, if the examiner has given polarity like this, then your VD is going to be minus of VM, right? Okay. So when you're taking, always take polarities in the direction of flow of current, right? That is, it's customary, right? Whenever you, it's not like current is flowing in one direction, you're taking polarities in other direction, and you keep getting all the negative numbers, right? So don't do that. Your current should be positive because everybody likes positive numbers, right? So we don't like negative numbers. So your direction of current and the polarity matches, you always get positive numbers. Okay. Okay. So let's solve this. So what happens during positive cycle? During positive cycle. During positive cycle, this is the direction of current for positive cycle. So now the current is going to flow through where? D1, is it not? Or still simple? So this is the same node here. You can take this as ground. So you have two resistors. So the voltage across the two resistors, 1K, 1K is Vin. Then what is V naught? V naught is going to be Vin by 2. V naught is going to be how much? Vin by 2, right? Half. V naught is going to be Vin by 2. And this resistor 2K is just going to come in parallel, right? So this, suppose this is node A here, node A, this node is A here, this node is A. It's the same node. This is the same node A. This is A, and this is A. Same node A. So what happens in the negative cycle? What happens in the negative cycle? During negative cycle, phi sin t, but now the direction of current has changed. The direction of current has changed, right? Now, when the current travels like this in negative cycle, it has two paths for it to flow, right? Naturally, it will choose both the paths because they are resistors. So it will travel like this and like this. Now the current through 1K will reach through the diode, but the current through 2K will also travel through 1K, right? So this time 2K and 1K, they are in a series, and the first 1K here is going to be across them, right? So this is a diode, 1K, two K and 1K, right? And see the polarities now. Polarities, you can see that the current is again traveling from plus to minus only, right? The same direction, plus to minus. So this is kind of a rectified output, the same direction. Can you see? If the polarities are matching, the polarities of the current and the voltage are matching, that means you always get positive numbers, right? So this node is, suppose this node is, right, what shall we call it? This is X and this is Y, right? So you still have the same node, X and Y here. This is X and Y. The current is still traveling from X to Y, right? Yeah, but what is voltage division now? V naught. V naught is going to be, this is V in. It is V in, okay. So V naught is going to be V in into 1K by 2K plus 1K. Is a negative number. So it's going to be minus V in by 3. So your V in has a peak of 5 volts. But what is happening in the positive cycle? You're going to get positive waveform, but it's V in by 2. V in by 2, so this is going to be 2.5 volt. This is V in by 3. So when there is negative, you again get positive. So this is V in by 3. So what is 5 by 3? 5 by 3 is 5 by 3. Okay. This is 5 by 2, right? 5 by 2. 5 by 2 is 2.5, right? 5 by 3. So what is V naught average? We have seen in a half wave rectifier, what is the average of a half wave rectifier? The average is going to be Vm by pi. But if you have one more cycle, it's like Vm by pi plus Vm by pi, it's 2 Vm by pi. But now here, the first duration is going to give you Vm1 by pi. The second one is going to give you Vm2 by pi. So Vm1 by pi is 2.5, 5 by 2. 5 by 2 by pi. And Vm2 is going to be 5 by 3 by pi. So this is going to be the answer, right? So calculator. What is the output? Five by 2, 5 by 3. 2.5, 2.5, 1.6, 0.5, 1.6. So, okay, so that's the number. So how much is this? Five by 2 by pi plus 5 by 3 by pi. This is the answer. Calculate. Two 2.5 plus 1.6, 4.1 by pi, something like that, right? Substitute the value of pi and get me the answer. So it's 1.326. Is it correct? Check. I don't have a calculator on hand. So there's a big positive cycle and a chota negative cycle. And why it became chota? Because of the voltage divider here is with 2K and 1K. In the previous case, the voltage divider is with 1K and 1K, right? So this is also a full wave rectifier output. But if you want Vm, what we have to do if you want Vm? Then in the place of 1K here, you have to put one diode, right? You know how to put in the same direction of D1. And in the place of 2K, if you put another diode in the same direction of D2, then the circuit becomes a bridge rectifier. But the gate examiner is clever, right? He took the same bridge rectifier and he knows that if D1 is on in positive, D2 is on in negative, you get full wave rectified output. But instead of diodes, he has placed resistors there so that the voltage is not equal to input. The voltage is going to get half or by 3 because of voltage division. Now, how do you calculate the power output average, the power dissipated in resistor? So what is power formula? Average power, 1 by T. What is P? P is I square R, all right? And then what we have to do? Now, can I write x as root x whole square? Any problem with that? The x as root x whole square. The value is still going to be same, right? So I'll make a root here. And then a square. So you can, if r is constant, you can remove it outside. Then what is this? This. Now this is the root 1 by t is the mean and then a square, right? So it is actually IRMS whole square into r is the power output average. So if you want average power output, you can have the RMS value of the current whole square multiplied by R, right? Find the average power dissipated in the 30 ohms resistor. This is also a gate problem. Find the average power dissipated in the 30 ohms resistor. So it's like the RMS value of current square R, right? Okay. What is IRMS for half wave? IRMS for half wave is going to be IM by 2. All right. IM by 2 for half wave rectifier, right? So how do you get IM? So what is the peak value here? VM is going to be 5 volt peak. The diode is on. So here you get I peak. So 5 volt is peak. So if you want peak at that point. So I peak or IM, call it IM, is nothing but 5 by 10 plus 20 plus 30. What is 10 plus 20 plus 30? 30 plus 20 is 50. 50 plus 1 is 60. 5 by 60 is IM. What is IRMS? IRMS is going to be 5 by 60 by 2. 5 by 60 by 2 is IRMS. Then what is your power output average? Therefore, power output average is IRMS square into R. So it is 5 by 60, which is the peak, by 2 whole square into 30. So how much is this? Okay, Roshan, right? You're saying 52.083. I'd go for it. 52.083. What's the units of power? Watt, right? Very good. 52.083. Right, I've not calculated, but I believe in the answer. 52.083 milliwatt. Good. Yeah, many 58.08 answers. 52.08. Yeah, that's correct. Perfect. Okay, so in all the problems that we have done, we have assumed that the diode is ideal, right? The diode is ideal, but we know that the diode is not ideal. It takes a drop of 0.7 before it compares anode voltage with the cathode voltage, right? So when the diode is comparing anode high, cathode low, it's not doing that if anode is slightly more positive. No, it says that anode should be 0.7 volts more positive than the cathode. So when it is comparing, we always took VA greater than VC, but the point is now a practical diode, if you take, it always demands a 0.7 drop across it. So for a half wave rectifier, you have a diode here and a resistor. Do you think your V0, this ID or the diode current, and this Vin, right? Now, do you think your V0 and Vin are same? No. The diode takes a drop of how much? 0.7. So when you sketch the output, how will the output be? This is Vin. Now, how do you sketch V0? How do you sketch V0? To sketch V0, till Vin touches 0.7, there is no output. So till 0.7, you don't get any output. You don't get any output. So your output is 0, 0, 0, 0 till here. Once Vin goes from 0.7 above, that is when the output starts. But what happens when Vin is 1 volt? If Vin is 1 volt, Vin, V0. If Vin is 0.7, your V0 is 0. If Vin is 1 volt, your V0 is 0.3. Vin is 2 volt, this is 1.2 minus 0.7, 1.3, right? 1.3. And your Vin is 5 volt, there's 4.3. That means the output is always trailing the input by 0.7. So when your Vin reaches 5, your V0 will reach only 4.3. So there is always a difference of how much? 0.7. The output always trails the input by 0.7 volts. So you can take, when this guy is 1 volt, this guy is only 0.3 volts, right? When he reaches 5, he's only 4.3. So the output is always less than the input by 0.7. Am I right? Now what happens if you have two diodes now, two diodes and then a resistor, you have Vin and V0, the output is less than the input by 1.4 volts because the diodes are in series. Each diode takes 0.7 drop. 0.7 plus 0.7 is 1.4. So in this occasion, when Vin is 1.4, that is when your V0 starts 0 plus. When Vin is 5 volt, there's only 3.6, right? So when you try to sketch the output, suppose this is the positive cycle here, right? So till your Vin touches 1.4 volt, there is no output. And after that, you get an output. By the time you reach 5 here, you're going to have only 3.6 here. And what is the difference between the two waveforms? The difference is going to be 1.4 this time. Right? So the output is always less than the input by how many volts? 0.7 volts, right? So you can. So this is the biggest disadvantage. And why did it happen? It happened because the diode current, because of the characteristics, the diode does not get on till it touches a voltage of what? 0.6 no output, 0.7, boom, the diode is on, right? The diode gets 0.7. Then your output is going to be 0 plus. So when your Vin is 1 volt, your V0 is 0.3 volt. The output is always trailing the input. It's always less than the input by 0.7 volts. So this is the characteristics between the VD and ID, right? Okay. Now, what happens if I have a signal V in Can you hear me? Can you hear me? Can you hear me? Okay. Yeah. Can you hear me now? Is my voice audible? Yeah. Now, carefully listen here. What I want to say is, can we have a diode whose characteristic is just 0.35? Or can we have a diode in this fashion, in this characteristics, right? So I want to shrink it to 0.35, or I want to shrink it to zero point 0.1, or I want to shrink it like this. Then I may not get this waveform, right? Now you might ask, how do I do it? Because this fellow takes 0.7 volts. What if I connect like this? And I put a resistor here. V in. Now, what is the difference between V naught and V in here? V naught is going to be V in minus VD, or V in minus 0.7 volts. Now I want to have an amplifier of gain 2. I want an amplifier of gain 2. I connect it like this. I want an amplifier just of gain 2. So what do you mean by gain 2 here? Gain 2. If this guy takes 0.7 volts at the output, if this guy is 0.7, to switch on the diode for operation, this guy is 0.7 divided by 2 is only 0.35. 0.35. Because what is VD? VD is going to be V naught by A. Right? So if I have an amplifier whose gain is 2, and then I do the same operation, what will happen? I might get a waveform where if this is your input, now this, but the moment it touches 0.35, what happens? Slowly 0, 0.1, 0.2, 0.35. The moment I give 0.35 into 2.7, bang, the diode is on. Once the diode is on, then there's some feedback mechanism. Your V naught and V in are related with your V naught is going to be V in minus 0.35. 0.35. So when you draw the waveform, it's at least going to come like this, where the difference is 0.35 now. Okay, that's good. What if I have an amplifier of gain 10? What if amplifier of gain 10? 0, slowly I start from 0. The moment I touch a voltage 0.07 here, the output goes 0.7 and the diode gets on. When the diode gets on, your voltage V naught is going to be V in minus of minus 0.07. So your V naught is almost equal to what? V in. So what I want to do is, you have drawn the characteristics between VD and ID. Your VD and ID, 0.7 volts is VD, and this is ID. What if we draw the characteristics between this ID and this VD, this ID and this VD, and I want to put the whole thing in a box, the whole thing in a box, and now I'm calling this whole box as a new diode, right? A new diode, this whole thing in a box, and the two terminals here in the current ID and VD, you realize that the characteristics is going to be 0.35 for VD, and this is my ID. What about this guy? What about this guy? He's got a characteristic which is going to be 0.07. Now, let's come for a practical op-amp. A practical op-amp has got a gain 10 power 6. What is the relationship between the VD and the ID for this box? For this box, I'm going to put this box, and these two terminals are my new anode and cathode. These two terminals are my new anode and cathode. I'll not show you what's there inside the box, but when you draw the characteristic, you realize that the characteristic has gone right here. Voltages Okay, can you hear me? Can you hear me?
Yes, sir. Yes, sir.
Can you hear me? Yeah. Okay, so you can see here that if the gain is 2, if the gain is 2, the input, the demand of input is only 0.35 if the gain is 2. But if the gain is 10, then to have rectification, the demand of input is only 0.07. What if the gain is 10 power 6? If the gain is 10 power 6, it can rectify voltages of Vin slightly greater than 0.7 by 10 power 6, almost 0. So that means 0.7 by AOL. What is AOL? Is the open loop gain. Open loop gain 0.7 divided by the open loop gain. 0.7 by open loop gain. 0.7 by open loop gain. So it can rectify all voltages Vn slightly greater than 0.7 by 10 power 6. Right? It's typically 0 volt or 0.7 micro. 0.7 microvolt. What is 0.7 micro? It is almost 0. What is 0.7 micro? It's going to be almost 0. Am I right? So here, somewhere here, having 0.7 micro. So this is almost like an ideal diode, right? So the whole structure is going to behave an ideal diode. So if somebody asks you, draw an ideal diode, how will you draw an ideal diode? So how do you draw an ideal diode? How do you draw an ideal diode? Right? I asked a student in an interview, right? Draw an ideal diode. You know what he did? He drew a diode and he wrote ideal. And he wrote ideal here, right? This is not what I expected. I expected to tell him that this diode should have two terminals, anode and cathode, but it should behave as if it is an ideal diode. So to draw an ideal diode, what we have to do is, these are the two terminals. One is anode, the other one is cathode. These are the two terminals, right? And you have to put it in a box. But what's there inside the box? Inside the box, you have something like this. Something like this. This is the anode terminal and the cathode terminal. So wherever you want an ideal diode, you can just remove it, connect it there. So wherever you want an ideal diode, you can just remove it and connect it there. Right? So this is our topic now. We are going to spend a lot of time on these type of circuits, right? What are these type of circuits? They also behave like rectifiers, but in the previous example, the comparison is done by the diode. The comparison here, comparison is done by diode. So whenever the comparison is done by diode, the diode is bribing us, right? It says, you give me 0.7 volts. You give me 0.7 volts, then I'll rectify. But op-amp is not like that. Op-amp says that, don't worry, for 0 plus, you give me 0 plus, I can start rectifying. You can start rectifying voltages of even very, very small value. So if you have an op-amp with the diode, then you can even start giving voltages like this. You can start giving, right, 0.1 volt signal to an op-amp, 0.1 into 10 power 6, that's a big number. So it can start rectifying even small voltages also for you, because it's going to work at 0 plus. But what happened for the normal diode? The normal diode is not giving you any voltage between 0 and 0.7. It's not giving any. So till 0.7, there's no output. But here, 0 plus, you can get an output. So this is our topic now. So this is just a motivation to start this topic. We're going to spend a lot of time on this topic. So this topic is called, what topic? This topic is called an ideal diode or precision diode. Ideal diode or precision diode or super diode. Ideal diode or precision diode or super diode. Right? So the same circuit, I'm going to draw it again. The same circuit, I'm going to draw it again in a textbook way of drawing, right? This, you don't find circuits like this in textbook. They draw it little clean, right? So they draw it like this in books. So this is how they draw. Ideal diode or precision diode or super diode. Okay, so let us go step by step. Let us go step by step, right? So who is a better comparator? Who is a better comparator? Comparison is done by diode here to compare anode voltage with cathode voltage. Now the comparison is done by op amp here. Op amp. So let us, to solve op amp with diode circuits, what we have to do is, first you have to treat procedure to solve op amp plus the diode circuits. What is the procedure to solve op amp and diode circuits? One, first treat op amp as comparator. Treat op amp as comparator. If this is V2, this is output. So if V1 is greater than V2, your VOP is positive, or V1 is greater than 0. What happens if V1 is less than 0? Your VOP is negative. Accordingly, you can see which diode is on and which diode is off. In some problems, your V1 might be grounded and input is given to V2 in some problems. Then what is VOP? What is VOP? Right? If V1 is greater than V2, your VOP is positive. Who is V1 here? 0. So if your Vin is less than 0, then your VOP is positive. What is the other case? If Vin is greater than 0, your VOP is negative. So let us have a thumb rule now. The thumb rule is, if the non-inverting voltage is greater, the output of op amp is positive. Accordingly, this VOP will drive some diode, right? So some diode, right? Whether the diode is like this or this, it doesn't matter. Suppose here I connect a diode like this, I connect a diode like this, right? Now tell me, which diode is on for VOP positive? Which diode is on for VOP positive? Here, your D1 is going to get on. Here, D1 is on, right? But if VOP is negative, then D2 is on accordingly, right? This is the first step. Sometimes the examiner might give two voltages. Here V in 1, here V in 2, and VOP. Then V in 1 should be greater than V in 2, then VOP is positive. Or V in 2 is greater than V in 1, then VOP is negative. So accordingly, right? So first step is treat op amp as comparator. This is step 1. Step 1. Step 2. Step 2. Step 2. Find the state of diodes. Find the state of diodes, which means on or off. Off. Apply virtual short only in negative feedback. Apply virtual short only in negative feedback. The last step is calculate the output V naught. Calculate the output V naught. Right? So this, you can easily know the state of the diodes if you replace the diode first. You remove the diode, treat op-amp as a comparator. Treat op-amp as a comparator, then you will know the state of the diodes. So now you tell me, how will you solve this question? How will you solve this? Okay. So now tell me, here I'm giving V in. Here there is a resistor R which is connected here. And here you have a diode. All right. Now, V in is here. Here you have the RL. This is VOP. Treat op-amp as comparator. Treat op-amp as comparator. So first case. So here you have 0 volts, right? Op-amp draws no current, this is 0. So if V in, if V1 is greater than V2 or V in is greater than 0, your VOP is positive. The diode is forward bias. Now, because this is a normal PN diode, you can replace the diode with 0.7 volts. 0.7 volts. You can replace the diode with 0.7 volts. Am I right? Now what happens in second case? Your VOP is negative. Diode is off. If diode is off, replace the diode with open switch. Now, let us calculate. Let us calculate. For calculation, we know that virtual short note can be applied only to case 1, right? Not case 2. Because in case 1, the circuit experiences negative feedback. So let's apply virtual short. If this is Vin, this node is also at Vin. If this is Vin, this node is also at Vin. Output follows input. But here, the current is 0 in the second case. So your output is also 0. So what will be the sketch now? If Vn is a sine wave, then what will be V naught? For all Vn positive greater than 0, your V naught is also equal to Vn. For Vn less than 0, your V naught is 0. V naught is output follows input. Here, your output follows input. Here, your output is 0. So this is a half wave rectifier. Now, who is doing all this? Who is driving the diode? Honestly, tell me, what is the difference in the diode circuit and this? The diodes used to drive, the diode is driven by input in those cases. But in op-amp case, who is driving the diode? It's the op-amp. How op-amp is driving? Can you see what is VOP now? What is VOP? VOP minus V naught. VOP minus V naught is 0.7. So your VOP is going to be 0.7 plus V naught, which is nothing but 0.7 plus V in. So who is going to supply the extra 0.7? Op-amp is going to supply that extra 0.7. So that means if my V in is 0, op-amp will give 0.7, 0 plus 0.7. Your V naught is 0 plus. If Vn is 1 millivolt, 0.7 plus 1 milli. Here V naught excuse me. Your V naught is going to be 1 milli. If this is 0.1 volt, 0.7 plus 0.1 volt. Here you're going to get 0.1. If this is 5 volt, 0.7 plus 5, which is 5.7. And here you're going to get 5. So can you see in every instant of time, who is supplying that extra 0.7? Who is driving that diode? It's the op-amp with the help of a source of power. That is why this is not a passive rectifier. It is an active rectifier. you give 0 plus, you're going to get an output. Now you can see that your output always follows input. Output always follows. So next time you want to draw a rectifier like this, how are you going to draw? You will simply say that your V naught will lie over this. Over this. It's going to lie. Your output follows input. But in the previous example, what happened in the previous example? In the previous example, you can see here in the diode problem, you can see here in the diode problem, the output and input is always trailing. The numbers you can see, there is always a difference of how many volts? 0.7 volts. There's always a difference of 0.7. But what happened in this case? In this case, who is driving this circuit? Who is supplying that extra 0.7? Is going to supply an extra 0.7. 1 millivolt, 0.7 plus 1 milli. 0.1, 0.1, 4, 4.7, 5, 5.7. So as long as op-amp does not saturate, it is going to supply that voltage. And the good news is, if I connect the same problem, what happens if I connect the same circuit and I put 3 diodes here? And I put 3 diodes here. 3 diodes. Again for Vin greater than 0. Again for Vin greater than 0. This is, you can take initially this voltage as 0 here. Zero VOP. Right? For Vin greater than 0, VOP is positive and all 3 diodes are on. When all 3 diodes are on, you are going to have here a voltage of 0.7 into 3, 2.1 volts. 2.1 volt. And what is V naught here? V naught. If this is Vin, this is also going to be Vin. Your V naught is again Vin, rectification. So what I wanted to say is, see how cleverly the designers have connected the diode. They have connected the diode in the loop where the op-amp can blanket that 0.7, that 1.4, that 2.1, even if you have number of diodes there, is going to cleverly blanket them, right? But having 3 diodes is a waste of time. But I just want to show how great is this circuit. Even if you put 3 diodes, it's still going to rectify. But what is VOP? What is VOP? Your VOP is going to be your V naught plus 2.1 or your Vin plus 2.1. So you can see how cleverly the op-amp is trying to blanket the 0.7, is going to cover him, protect him in that loop, such that the output is always a function of the input. The output is always the function of the input. Are you getting, right? So please, I repeat, for these kind of problems, what is the procedure? The procedure is always treat op-amp as a comparator. Just remove the diode and draw the circuit separately. Have patience. Just remove the diode, draw the circuit separately, right? And then simple logic. If plus voltage is more than minus, your VOP is positive. If minus is more than plus, VOP is negative. Accordingly, now you have to know the nature of the diodes, right? But once the diode is on, after knowing the state of the diodes, you have to apply negative feedback only when the diode is on and it's able to backtrack. See here, it do the comparison from the input, from the output to the input. There is a flow of current, so it can backtrack now, right? We know op-amp can source or sink, it doesn't matter. But once VOP gets positive, the diode is on. Once the diode is on, there is a possibility of backtracking. So you can apply virtual ground because of negative feedback, but you cannot apply virtual ground in case 2. Why you cannot apply virtual ground in case 2? Because the diode is off. There is no possibility of comparison from the output to input. So the voltage cannot increase, decrease, increase, decrease. So that comparison cannot be done in second case. So when there is no negative feedback, you cannot apply virtual ground. Now what happens here? Here the VOP is going to be, what is VOP? Is going to be, it's a large negative voltage, large negative, which means it is minus VSAT. It's a large negative voltage. It's going to be minus VSAT. The op-amp VOP is going to be 0.7 plus Vin in first case. In the second case, the VOP is going to be minus VSAT with a negative voltage. With a negative voltage, do you think with a negative voltage at this point, do you think the diode can be on? No, the diode cannot be on. The diode is on only for what voltage? VOP positive, but not VOP negative. VOP positive, diode on. VOP negative, the diode is off. VOP positive, the diode is on, but for VOP negative, the diode is off. So what is the limitation in this circuit? Limitation. When the input signal goes from
sir, hello sir.
yes,
Sir, మీ వీడియో మ్యూట్ లో ఉంది సార్. సార్ ఆన్ చేయండి సార్.
అంటే ఇప్పుడు వీడియో ఆన్ చేస్తే అది ఇదవుతుంది,
ఆహాహా.
ఏమంటారు, బ్లర్ అవుతుంది, ఇంటర్నెట్ కనెక్షన్ స్లో ఉన్నట్టుంది.
ఓకే సార్, ఓకే. అదే స్టూడెంట్స్ మెసేజ్ పెడుతున్నారు అనమాట, కామెంట్ చేస్తున్నారు. ఓకే సార్, ఓకే.
When the input signal goes from positive cycle to negative cycle, the op-amp output should suddenly switch from 0.7 plus Vin to minus Vsat. 0.7 plus Vin to minus Vsat. You can see here, it is going from 0.7 plus Vin VOP to minus Vsat. This sudden change can introduce distortion at output. Distortion at output. Then how to avoid? How to avoid? Connect two diodes in the feedback path. And do not allow op-amp to saturate. So how are we going to do this? From now onwards, what is the discipline? We are going to connect diodes like this. If there is one diode like this, we are going to connect another diode like this, right? If one is on, the other one will be off. If this is on, this one is going to be off. From now onwards, we are going to connect diodes in this fashion where this node will see anode as well as cathode to complete a loop, right? So either this or this will complete a loop, right? So how are we going to improve this? How are we going to improve this? From now onwards, whenever you draw any circuit, always see that there are two diodes in the feedback path and do not allow op-amp to saturate. Should always have two diodes in the feedback path and never allow op-amp to saturate. See, it's not that you should always connect it to non-inverting only. You can as well connect it to what terminal? Inverting also, because this happens to be the gate problem, right? So we'll do both. You can have non-inverting. Oh, sorry. Not neat. So this is also a gate problem. Many a times they have asked this. Now you can see here. Now you can expect what is VOP. So this is a clever way of connecting. If VOP is positive, D2 is on to give negative feedback. If VOP is negative, D1 is on to give negative feedback. So if it is negative, when negative is connected to cathode, the diode is on. When positive is connected to anode, the diode is on. So at any instant of time, only one diode is on. So you can still get rectification from here, from this, but you will never allow the op-amp to saturate. Because when suddenly op-amp output goes boom to plus 12 or minus, at the zero crossing of the signal, when the signal crosses these points, you might get, distortion suddenly when it switches from positive cycle to negative. So let me read this one. Connect two diodes in the feedback path and do not allow op-amp to come back. We'll take a break. When we come back, we will see more of these ideal diode circuits, right? Take a break. Take a break. Take a break. Take a break. కట్టండి అతను. వెంకట్, నేను కనబడుతున్నానా?
అవును సార్, అవును కనిపిస్తున్నారు సార్.
వాయిస్ బ్రేక్ అవుతుందా?
లేదు సార్, బాగానే వస్తుంది.
ఓకే, వీడియో ఆఫ్ చేయను అయితే నేను.
వీడియో కూడా బాగానే వస్తుంది సార్ ఇప్పుడు.
బానే వస్తుందా?
అవును సార్, అవును.
ఓకే. వెంకట్, ఇప్పుడు పనిచేస్తుందా? వెంకట్, వెంకట్, వెంకట్. Are you able to hear?
காஃபி வேணுமா
ஆ.
அபி உனக்கு வேணுமா ஏய்.
అభి కంప్యూటర్ వద్దా
வந்துச்சு I just
are you able to hear
yeah.
వెంకట్ వినపడుతుందా వెంకట్ థ్యాంక్ యూ సో మచ్
Welcome.
Okay. Let's get started. Thank you. Yeah. Now, just to have a difference, in the previous problem, I have given V in to the non-inverting terminal. But now I'm giving V in to the inverting terminal, right? Just to have a change. So for inverting, I told you, when the input voltage is positive, the output will be negative. If input is negative, the output will be positive, right? Because the input is given to the inverting terminal. But in the first problem, input is given to the positive terminal. So what will happen? If the V in is positive, your V naught is also going to be positive, or VOP is going to be positive. If V in is negative, your VOP is going to be negative in the previous case. But in the present case, input is given to inverting terminal. So let me draw it like this. So my first step is treat op amp as a comparator, right? As a comparator. When you treat him as a comparator, just open circuit all the diodes, just remove the diodes, right? Only input. So this is ground. Here we have V in, and this is VOP. Now tell me, if the voltage at inverting is more than non-inverting, if V in is greater than 0, your VOP is going to be negative, right? Suppose this is V1 and this is V2. What happens if V2 is greater than V1? VOP is negative. If V in is less than 0, your VOP is going to be positive. Now, accordingly, we have to see which diode is on and which diode is off. If VOP is negative, when negative is connected to anode and the negative is connected to cathode, which diode is going to get on? So in this case, first case, VOP is negative, D1 on and D2 off. Whereas VOP is positive, now D2 is on, but D1 is off, right? So let's have two circuits now, two equivalent circuits. One is case 1, V in positive, VOP negative. VOP is negative. Which diode is on? D1 on, D2 off. If D1 is on, the diode that is on is replaced with 0.7. The diode that is off is replaced by an open switch. This first case. This is the equivalent circuit, right? What is happening in second case? If V in is less than 0, or V2 is less than V1, or V1 is greater than V2, your VOP is positive, right? Case 2. If V in is negative, your VOP is positive. If V in is negative, your VOP is positive. So D2 is on and D1 is off, right? D2 is on and D1 is off, right? V in is less than 0 in this case. Now, what is the equivalent? So your D2 is replaced with 0.7. Right? So previously, this was D2. Now D2 is on. and D1 is off. Now see here, because very cleverly they have connected the two diodes in a fashion that at least one is on and there is a possibility of negative feedback. So negative feedback persists here both for case 1 and case 2. Case 1 and case 2. But in the first problem before the break, we have seen that there was only one diode, and when VOP was negative, the diode was off. The diode was off, right? Okay. So now the last step is calculation. Calculation. So let us do the calculation. We have the equivalent circuits now. Let us do the calculation. Because of negative feedback, again, you can apply virtual short, ground. This is VOP. This is VOP, right? This case 1 calculation, case 1. Now tell me, what was VOP when D2 is off? When D2 is off, right? If this is ground, what is this node? Yeah, this is also 0, right? This is also 0. Okay. Now, what is the voltage of ground? What is the voltage of ground? This is also 0. Okay. So you have 0 here and you have 0 here, right? Then what will happen to the current I here? I. Now, what is Ohm's law? Current will flow only when there is a potential difference, right? So if this is 0 and this is 0, so there's a current of 0 minus 0 by R plus RL. 0 minus 0 by R plus RL. So your current is 0, your I is 0 here, and your V0 is also 0, right? Okay, your output is 0. But what is VOP? VOP. But is it at minus VSAT? Like what we have seen in the previous case, minus VSAT, the op-amp was boom, suddenly saturating? No. It stuck one diode drop below now. Because what is 0 minus VOP? 0 minus VOP. The potential difference. This end is 0, this end is VOP. 0 minus VOP is 0.7, or your VOP is minus 0.7 volts. Thank God, right? So your VOP is minus 0.7. It is not minus VSAT anymore. The diode is off, you're getting rectification, no output, but still your VOP is not minus VSAT. It is minus 0.7. Okay. What about the calculation for case 2? How will you calculate case 2 here, right? Okay. Again, there is a possibility of backtracking. So if this is ground, this node is also at 0. This ground, this node is also at 0. Okay, so let's apply KCL. Entering current is equal to leaving. So your Vin minus 0 by R is 0 minus V0 by R. Okay, this looks to be like an inverting amplifier, right? So your V0 is going to be minus Vin. Your V0 is going to be minus. In the previous case, we had V0 Vin, V0 0, but here, okay, it was expected because the input is given to inverting terminal. So the rectified output, you're going to get minus Vin. Okay. But what is VOP, by the way? VOP. VOP. So again, VOP minus V0 is 0.7. And what is minus V0? VOP is going to be 0.7 plus V0. But V0 is minus Vin. It's 0.7 minus Vin. See, the examiner in these type of problems, somehow he likes VOP. He doesn't ask V0, right? Because the moment you see a problem, you know it's rectified, right? He intentionally asks VOP. So what is the struggle of op-amp to rectify this? The struggle of op-amp in the previous case was shooting up to minus VSAT from 0.7 plus Vin. But the op-amp output is just shifting between minus 0.7 to 0.7 minus Vin. Minus 0.7 to 0.7 minus Vin. Minus 0.7, minus 0.7 in this case to 0.7 minus Vin here. Okay, then what is the output? What is the output? What is the output? what is the output? The output is for all Vn greater than 0, your V naught is 0. For all Vn greater than 0, your V naught is 0, right? Vn greater than 0, your V naught is 0. Second case, for all Vn less than 0, your V naught is, what is your V naught? V naught is minus V. So this is the final summary here, right? So for all Vn greater than 0, your V naught is 0. What do you mean by greater than 0? Positive cycle. What do you mean by less than 0? Negative cycle. So when Vn is less than 0, your V naught is minus of that negative voltage. Suppose, give me some negative voltage. So -1, -2, -3, right? If Vn is -1, V naught is minus of -1, that's +1. If Vn is -4, V naught is minus of -4, it's plus. So when Vn goes negative, your V naught is going in the positive direction. So here it is 0. So in this duration, your V naught is 0. In this duration, your V naught is minus V, right? Okay, so this is also a half-wave rectifier, but because the input is given to inverting terminal, the input is, even the rectified output, you can see there is a 180 degrees flip. The negative cycle is not negative, the negative cycle has become positive. But okay, the positive is 0, but the negative, you have flipped it. So it's no doubt unidirectional. So it is still a rectifier. It is still a rectified output, right? And what about the transfer characteristics? Transfer characteristics. How will you draw the transfer characteristics? For all Vn greater than 0, your V naught is 0. So your Vn is 1 volt, V naught is 0, Vn is 2 volt, V naught is 0. So your V naught is 0. But if Vn is negative, your V naught is positive. Suppose your Vn is -1, your V naught is going to be +1. If Vn is -2, your V naught is going to be +2. Right? So this, if you join them, you get this line. Right? So we have shifted to the second quadrant now. So it means that there should be an active device which does this. The op-amp is responsible for all this, right? Find V naught and VOP. If VD on is 0.7. Find V naught and VOP if VD on is 0.7 volts. Find V naught and VOP if VD on is 0.7. Find V naught and VOP if VD on is 0.7.
தண்ணி வேணுமா?
Okay, so by inspection, we know that there is only one voltage in the first problem, one voltage in the second problem, but two voltages for comparison in the third problem, right? So what is the difference in the first problem? The voltage that we are giving, I've given it to non-inverting. In the second problem, the voltage is given to inverting. In the third problem, we have two voltages, one at non-inverting, the other one is inverting, right? Okay, but whatever it is, we have to know the behavior of a comparator, right? So what's a comparator operation when you have a single voltage? You have a single voltage. 2 volts. Are there any voltage here? If you open circuit the diode and see, right? So this is, the op amp has to be a comparator. So there's nothing here. This is ground. Yeah. So it's seen that 2 volts is connected to non-inverting. When a positive voltage is connected to positive terminal, your VOP is positive. Your VOP is positive. Now, if you connect a diode like this, what is the nature of such a diode? The nature of such a diode is the diode is going to get on. The diode is going to get on. But what is VD on? VD on is VD on is going to be 0.7 volts. 0.7 volts. 0.7 volts. Now, what is the output? The output is 1 plus R2 by R1. But if I directly say 1 plus R2 by R1, some students may not believe. They say that, what happened to 0.7? The 0.7, I'm telling you, it's been very cleverly blanketed by negative feedback. So the op amp is very, very securely stuck. The diode is stuck there. Now the diode, you're putting that diode in a surprise. The diode thinks that just before the break, when we were doing all the clipper circuits, he's the one who's going to give 0.7 drop, right? But now what op amp is telling him, right? Diode, you stay in a place where the output will never be a function of this 0.7, right? I don't want to see 0.7 drop hereafter in the problems. You will have 0.7, but that 0.7 is a function of VOP. It's not a function of V0. So it's been very cleverly blanketed in negative feedback, right? So this is 2 volt. What is this voltage then? This is also going to be 2. The inverting, you can apply KCL. You can apply KCL. What is KCL? 0 minus 2 by 1K is 2 minus V0 by 2K. So your V0 is going to be 1 plus 2K by 1K times of 2. So this is the same problem. So that means we have designed a circuit in such a fashion that we still get the non-inverting amplifier with the diode, right? But the 0.7 should not come into picture. So you have to, please don't connect the diode in series with 2K. We will spoil the whole circuit, right? Don't connect the diode in series with 2K, right? It's not, that's a log amplifier. That's a different circuit. So we'll discuss that later in the nonlinear applications, right? So what is the voltage here? 1 plus 2 by 1 is 2. 2 plus 1 is 3. 3 into 2 is 6 volt. It's going to be 6 volt. And what is VOP, by the way? What is VOP? How much voltage the op amp is supplying to set up virtual ground. To bring back this 2, the op amp output has to run to what voltage? So he has to run VOP minus V0 is 0.7. The difference is 0.7. So what is VOP? It is 0.7 plus V0, which is 6. So the op amp output has to settle at 6.7. Now you tell me why op amp will go there to 6.7. How does op amp know? He doesn't know. If we have seen op amp output going to 1 plus RF by R1 to set up virtual ground, going to minus RF by R1 to set up virtual ground. Now op amp has to go to 6.7 only to set up the 2 volt there. If he's any other voltage other than 6.7, he's going to become restless, and the error between the 2 terminals will converge only when there is 2 volt here. If you say this is 2, we have to say that the output is at 6. If you say that the output is at 6, the op amp, bang, 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 it has to settle down at 6.7 volt, right? If you put 2 diodes in series, it is 6 plus 1.4. The op amp has to settle at, what is 6 plus 1.4? 7.4 volt, right? If you put 3 diodes here, the op amp, to set up virtual ground, bang, 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 he has to settle at 6 plus 3 diodes, 2.1. 6 plus 2.1, 8.1 volt. Are you getting, right? So the op amp output can be 1 plus RF by R1, minus RF by R1, anything. He will not sleep until He brings back that negative terminal. But to do that, remember, you should give negative feedback. There should be a flow of current in that loop. Negative feedback means nothing. There should be a flow of current from the output node to from the output node to the inverting terminal. There should be some sort of signal transfer there, right? Okay. So the positive voltage 2 volt, the output is going to be 1 plus 2k by 1k into 2, that is 6, and the op amp output has to settle down at 6.7. Fine. What about the second one? What about the second problem then? What about the second one? When a positive voltage is given to negative terminal, what is happening when a positive voltage is given to negative terminal? This is V1 and V2. Tell me, if V1 is greater than V2, your VOP is positive. If V2 is greater than V1, your VOP is negative. So who is greater in this case? Who is greater? Your V2 is greater than V1. So your VOP is negative is true, but this is false, right? Your V2 is greater than V1. 3 volt. Who is large number? 3 or 0, right? 3. 3 is a big number than 0. So 3 is greater than 0. Your output is negative. When it is negative, naturally, this diode is on. This diode is on, right? So when the diode is on, what is the drop across the diode? The drop across the diode, be careful with the diode here, right? 0.7 is the voltage between anode and cathode. This is 3K. So because the diode is on, there is a flow of current. The diode is on, there is flow of current. You can still apply what ground? Virtual ground. Entering current equal to leaving. Am I right? What is entering current? 3 minus 0 by 1K is 0 minus V0 by 3K. So your V0 is going to be the inverting amplifier gain minus RF by R1, R2 by R1 into 3. That's going to be minus 9 volt. It's going to be minus 9 volt. Now, what is VOP? What is VOP? So this time, what is the difference? Your V0 minus VOP is 0.7. Your V0 minus VOP is 0.7. So what is VOP? VOP is going to be V0 minus 0.7. Your V0 is already minus 9, minus 9.7 volt. Your VOP is going to be minus 9.7 volt. What for? To set up virtual ground. Why op amp will set up virtual ground? Because there is a negative feedback. How do you know there's negative feedback? Because the currents are flowing in that loop, right? The currents are flowing. The diode is, when the diode is on, naturally there'll be a current. And what about op amp? Op amp can send current in any direction. It can source or sink. As long as the diode is on, there is a signal processing done in that feedback loop. right? So your V naught is minus 9 and your VOP is minus 9.7, minus 9 and minus 9.7, right? So in all these problems, we are assuming that the supply voltage is much larger than the output, right? So that means the supply voltage is at least plus 12 or minus 12, because we don't want to spoil the circuit. We don't want to spoil the circuit. We don't want to saturate, right? Okay. Okay. Yeah. Now what happens in this case? You have 3 volt here and this end is 1 volt. VOP. So now tell me which diode is going to get on? Which diode? Is it D2 or is it D1? Tell me which diode is going to get on here? D2 or D1? D1, very good. Very good. D1 is going to get on, right? Because VOP is positive, D1 is going to get on. So what is the equivalent now? The equivalent is you have 3 volts. There is 1 volt here. D1 is going to get on. D2 is off. And you have 2K, right? Now what is VOP? If this is 3, this node is also 3, right? If this is 3, this node is also 3. So VOP minus 3. VOP minus 3 is 0.7. 0.7 volts. So your VOP is going to be 3.7. 3.7 volt. 3.7. Now tell me if this is 3, what is this voltage here? It's going to be 3. It's going to be 3, right? I just included RL here, but in the gate problem, there's no RL. What happens if RL is not there? If RL is infinite, if it is a gate problem, if RL is infinite, then what is your V0? Your V0, if RL is infinite, there is no current that is going to flow through 2K because it's an open circuit. Your V0 is going to be 3 volts. 3 volts. But now because this is at higher potential, 3, and this is at lower potential here, ground, definitely there can be voltage division, right? If RL is finite, then what is your V0? Your V0 is going to be 3 into RL because RL is not given, right? So you can apply voltage division 3 into RL by 2K plus RL, or V0 is going to be 3 into RL by 2K plus RL, right? So if RL is large value, what happens if RL is very large, RL is infinite, your V0 is 3. This is a gate problem. So V0 is going to be 3 volt if RL is not there, right? And what is VOP? VOP is going to be 3.7 volt. What for? To set up virtual ground. To bring back the same voltage there, it has to set up virtual ground. And that's the reason it is 3, right? It's 3 and the output is 3.7. And all of you, what is the current through the diode? What is the current through the diode? D1. What's the current through the diode? Suppose I want to find the current here, ID1. What is ID1? If I would have given in the problem, what is ID1? What's the current through the? Because as you rightly mentioned, D1 is on, but D2 is off. What is ID1? This current, if RL is not there, this current is going to travel through here. Are you getting? This current is going to travel, if RL is not there, the whole current is going to travel here. So it's going to be 3 minus 1 by 2K, it's 2 milliampere. If RL is infinite, V0 is 3 volt and ID1 is going to be, how much is ID1? This current is this 3 minus 1 by 1K. 3 minus 1 by 1K, it is 2 milli. It is going to be 2 milliampere. Right? If RL is infinite, V0 is 3, and the whole current now is there at the inverting terminal, 3 minus 1 here, right? How do I know? I don't know. I'm just applying KCL here. At this node, entering current is equal to leaving. At that node, entering current equal to leaving. This current, if RL is infinite, is 0 in that problem. So op amp draws no current. So the same current has to travel through 3K and 1K, right? 3K and 1K. So ID1 entering is equal to leaving. So it is 2 milliampere, right? Right? So what is the diode D1 current here? This current has to split into two currents. If RL is infinite, like in that gate problem, this current is almost 0. So this whole current has to come here, but op amp draws no current, it has to travel. Are you getting? So ID1 is a current through 1K if RL is infinite. Okay. Sketch V0. So some resistors we have connected, you can take 1K here, 2K here, 3K here, 4K here, right? This VOP, the first op amp, have T1, T2, this V0. Sketch V0, given VD on equal to 0.7 volts. So remember, if negative feedback is there, one more thing you would have observed, whenever negative feedback is there, the output is independent of RL. The output is only function of input, is independent of RL. But once the diode is off, the op amp is disconnected, there is no negative feedback, so the load is somewhere hanging. So the output has become a function of RL there. So that's a pity there, right? The output has become a function of RL, right? But that should not happen. So if the output node through the op amp, if it is in negative feedback, then your output will always be independent of RL, right? There's a discontinuity there because of the diode. Otherwise, we never get, that is why the examiner never gives RL for this problem, right? The output is now a function of RL, so that's nonsense. Why it became a function of RL? Because the D2 is off. There's a discontinuity between the output and the output VOP and V0, right? Had there been a diode here, your output will always be a function of the input, right? So that is expected in an amplifier. Your output should always be a function of input, right? RL should never come into picture. So that's a bad way of designing, right? It's just a problem. It's just a problem. So it doesn't matter. The examiner was interested not in V naught in that problem. He was interested in VOP. He was not interested in V naught. He said, what is VOP? What is VOP? The right answer is 3.7 volt, 3.7 volt, right? Yeah. So please, a clue to start the problem. The clue is, I want you to draw two equivalents. I want you to draw two equivalents. Two equivalents. One is for so what is the clue to start the problem? I want you to draw two equivalents. V in positive. When a positive voltage is given to positive terminal, the VOP is positive. There's only one input to the positive terminal. V in positive, VOP positive. V in negative, VOP negative. So two different circuits you have to draw. V in positive, VOP positive. Which diode is on? Which diode is on for V in positive? D2. Replace D2 with 0.7 and D1 with open switch. That is one diagram. The second diagram says V in negative, VOP negative. If VOP is negative, D1 on, replace D1 with 0.7 and D2 with open switch. So I want you to draw two equivalents now. Two equivalents. Case 1, V in positive, VOP positive. If VOP is positive, which diode is on? D1 off, D2 on. D1 off and D2 on, right? Okay, so this is first case. Am I right? So what is the calculation for this? Calculation. What's the calculation? Here there is a current flow, there's a current flow, there's a current flow. The current is not cut, right? So there's a flow of current in both the op amps in the loop. So definitely it is setting up virtual ground. So if this is V in, if this is V in, this node is also V in, right? This node is also V in. Now you can apply KCL, entering current is leaving. But the good news is this op amp, the second op amp here, does not draw current. So the same current is going to travel till here, V naught, right? So what is KCL? 0 minus V in by 3K equal to V in minus, if I know this node, it's okay, but I don't know this node. So I can write V in minus V naught by 1K plus 2K. 1K plus 2K. So your V naught is going to be 1 plus 3K by 3K. So it's going to be 2V. Your V naught is going to be 2V. Now, Just tell me, between V in and 2V in, your V naught is 2V in, what will be this node? What will be this node Vx? Find Vx. V in minus Vx by 1k equal to Vx minus 2V in by 2k. Okay, so you'll find Vx. If this is Vx, this is also Vx. And then you can find VOP also. You can find VOP. Of course, my job is to sketch V naught, but I'm just telling you what is VOP. So your VOP minus Vx, VOP minus Vx is 0.7. So your VOP is going to be 0.7 plus Vx. 0.7 plus Vx, right? As a homework, what is Vx? V in minus Vx by 1k equal to Vx minus V naught. V naught is 2V in by 2k. 2V in by 2k. So tell me, what is Vx? 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 Right? So your VOP is going to be 0.7 plus Vx. So your V naught is 2V. Your V naught is 2V, right? So if V in is positive, V in is positive, your VOP is also positive. Here we have D2 and here we have D1, right? So who is on? D2 is on and D1 is off. D1 is off. So what is the middle voltage here? The middle voltage Vx is going to be between 1 and 2, between V in and 2V in. So between V in and 2V in, between 1 and 2, some number, 1.3, right? 4 by 3. So some students are saying 4 by 3, right? 4 by 3. Okay, so there's 4 by 3. So if this guy is 4 by 3, 4 by 3 is like 1.33. So this is also 1.33. So your V naught is going to be 1.33 plus 0.7, so almost 2, right? Okay, good. This is for case 1. What about case 2? Case 2. V in negative, VOP negative. If VOP is negative, which diode is on for VOP negative? D1 on and D2 off. D1 on and D2 off. Now the good news is still there is virtual ground in both op-amps. Why there is virtual ground in the second op-amp? Of course, there is 2K here, so there is virtual ground. How there is virtual ground in the first op-amp? There is that 0.7 volts that is on, so again there is virtual ground, right? So what about the calculation? So if this is V in, this node is also V in. Okay. But because they have split, what is the current I here? 0. Now, according to Ohm's law, if the current is 0 through a resistor, what is the voltage? What is the voltage? Ohm's law, right? V equal to IR. V equal to IR. The current is 0, so the voltage here is also 0. So this node is 0, right? Now, with no waste of time, tell me where you will apply KCL to find V naught. You have two options. You can apply at this node Vn or this node 0. If you apply at Vn, you can only calculate the diode current because entering current, so you can see entering current is equal to leaving current because op amp draws 0 current, right? So there's a current entering, there are 3 currents leaving, right? So this is through 3K, this is through 1K, this is through the diode, and this is through the op amp. So our job is not to calculate the diode current, our job is to calculate V naught. So my suggestion is apply KCL at this node, KCL at the 0 volts node. Then you can quickly find what you call the output, right? So it's Vin minus 0 by 1K is 0 minus V naught by 2K. Your V naught is minus 2 Vn. So what is the final result? The final result. If Vn is greater than 0, your V naught is 2 Vn. Am I right? If Vn is less than 0, your V naught is minus 2 Vn. Your V naught is minus 2 Vn, right? Now just tell me what is a diode current? Entering current is 0 minus Vn by 3K. Leaving current, if you want the diode current. So why we should not apply KCL at Vn? If you apply, you get diode current, you don't get V naught, right? So suppose you say, no, sir, I want to apply. Okay, 0 minus Vn by 3K equal to Vn minus 0 by 1K plus ID1 plus 0. So what you'll do with this? Tell me. You'll substitute Vn and you only get the diode current here. You only get the diode. I don't want the diode current. What I want is V naught. So if you want V naught, it's intelligent that you need a node which relates Vn and V naught. So there. Now check. At 4 volts. Your V naught is 2 E. If Vn is minus 2, your V naught is minus 4. V naught is minus 2E. The inverting and the non-inverting. But now by adjusting the values of resistors, you can get a different gain that you want, right? So please calculate as a homework, just substitute V in here and get me ID1, right? You can get me ID1 here, the diode current. So Vx is 4 by 3 V in and VOP is 1.33 V in. Very good. Very good. Okay. So we have seen different kinds of problems. The first problem, we had a DC voltage given to only one terminal. The second problem, we had a DC voltage given to the minus terminal. In the third problem, we had DC voltage given to both the terminals. Now we have an AC signal, a sine wave being given to one terminal, right? What if I give an AC signal to one terminal and a DC to the other voltage, right? So we are like all combinations of problems. So in case if I give a AC to one and a DC to the other, and let V in be a triangular input of 10 volts peak, and the threshold here is going to be the other terminal -5. So you have a comparison where V in is greater than -5 and V in is less than -5. So you can have two cases. The op-amp does not know that you're given a triangular or any waveform. He is just a comparator in the initial stage. So what a comparator will do, it just compares V in with -5, where V in is greater than -5 or V in is less than -5. What happens if the non-inverting is greater than inverting? What happens if the non-inverting is greater than inverting? Your VOP is positive. If the inverting is greater than non-inverting, your VOP is negative. Your VOP is going to be negative. So sketch V0, VD on is 0.7. Okay, so the story remains same, right? So the story still remains same. I should tell you, treat op-amp as what? A comparator -5. And here with the resistor, you have V in, and there's VOP. So I have to tell you the two cases. V plus is greater than V minus, VOP is positive, right? Which means -5 greater than V in, your VOP is positive. If VOP is positive, who is on? Who is on? VOP is positive, D2 on, and D1 off. There's one case. What is the other case? If V minus is greater than V plus, your VOP is negative. If V minus is greater than V plus, your VOP is negative. So negative, if V minus, your V in greater than -5, your VOP is negative. So if VOP is negative, who is on? D1 on and D2 off. So you can draw two diagrams, right? So two diagrams and then finish it. This is case one and case two, right? So you can have case one and case two. Treat op amp as a comparator. As a comparator. Okay. So tell me, what are the cases? Case one, case two, D1 on, D2 off. What is D1 on? Which case is D1 on, D2 off? Case two, okay. Case two, Vin is greater than minus 5 volt. Vin is greater than minus 5 volt. D1 is on, VOP is negative. D1 on, D2 off. So now tell me, because there's negative feedback, virtual ground, this node is at minus 5. This node is at minus 5. Now, do you know that current always needs a closed path to travel? Yes or no? Can you form a closed path through this, the current through this resistor? Can this current through the resistor go round and round and round the circles? No, current is 0. So your V0 is going to be minus 5 volt. Your V0 is same voltage. Or what is the current I here? The current I is going to be minus 5 minus V0 by 2R. But I is 0. 0 equal to minus 5 minus V0 by 2R. Your V0 is going to be minus 5 volt. When there is no current, the whole voltage is going to get manifested. This case 2. Case 1. What happens in case 1? If Vin is less than minus 5, your VOP is positive. If your VOP is positive, then D2 is on and D1 is off. D2 on and D1 off. D2 is on. So D2 is on and D1 is off, right? So now you can apply virtual short, minus 5, entering equal to leaving. V in minus of minus 5 by R equal to minus 5 minus V0 by 2R. Okay. Cross multiply, right? Cross multiply. So 2Vn plus 10 is minus 5 minus V0. R gets cancelled. So what's V0? V0 is going to be what is V0? Minus of 2Vn plus 15. numbers V in, V naught. If V in is -5, V in is -5. If your V in is -5, what is V naught? -5 into 2 -10, 15 -5, right? So it starts from there. If V in is -8, -8 is 1. If V in is -10, +5. So this is how V naught and V in are changing, right? So tell me, for all V in greater than -5, your output is -5. For all V in greater than -5, this is a portion greater. For all V in just above the line is called is less. Some sort of linear relationship. When V in is -8, your V naught is +1. When V in is -8, when V in is -10, your V naught is going to be +5. When V in is -10, your V naught is going to be +5 here, +5. Let me, because to draw a line, 2 points are enough. Why should I take all the points here? 2 points I'm taking. These 2 points I'm taking. This point and this point. -5 -5 is 1. -5 -5. The other one is -10 +5. This is -10. It's going to be at +5. So there's no need for us to take all the other values here, right?
Hello, sir. Hello, sir. Can sir?
వినబడుతుందా?
Okay.
Yeah. Can you hear me? You can ask doubts. Please unmute the students, please.
Class అయిపోయిందా?
9 అయింది కదా టైం.
ఓకే.
9 అయింది నాన్న.
సరే సరే.
Hello.
Yeah.
Good evening, sir. I'm not understanding how the current is zero. I'm just confused.
Current is 0 where?
When Vn is greater than minus 5 volt.
Acha, in the previous problem?
In the same problem, sir.
Yeah. Vn
Yes,
is
sir.
greater than minus 5 volts. Yeah. See, this is something I have been telling you. Can you see what I'm writing here?
Yes, sir.
Can you see? This is my 5 volt or minus 5. Here I have 2R. And what is the voltage V naught here? So there's no current here. Current needs a closed path to flow. So your V naught is minus 5 only.
So basically we don't take V naught minus 5 by 2. Only we take only if it is in closed path.
No, see, it's always debatable. Suppose if you say that current is 0 or not 0, how Ohms? I am proving it by Ohm's law. I am saying I is V1 minus V2 by R. But if the current is 0, why the current is 0? Because the current needs a closed path to flow.
Yes, sir. Yes, sir. Got it, sir.
Are you getting?
Yes, sir. If
Good,
there is
good,
if there is a load resistance, then it will
Yes,
form a
then
closed
you are right,
path.
you are
Then
right,
I'll
you are
get a
right.
current. Yes,
Yeah,
sir.
you're right.
I was just confusing in this point due to some voice disturbance.
No.
We missed it. Thank you, sir. Now I got it, sir. Thank you.
Yes.
Hello, sir. Hello.
Hello.
Hello, sir.
Yes.
Hello, sir.
Yeah.
Good evening, sir.
Yeah. Good evening.
Sir, 28th slide, sir.
20.
Hello, sir.
Me?
Sir, can you go to 29F, sir? Sir. Hello, sir. Can you go to 29F? Sir.
See, in the comment section, there is some student, Santosh Malik. He said, why I don't have a hand raising option? Is that hand raising? He doesn't have a hand raising option.
Sir, can you go to 29F, sir?
28. This is the 28th one.
I am seeing doubt actually.
Yeah.
Sir, here how to get V naught, sir?
How to get V naught?
That RL is infinite. I didn't get, sir.
No, in the problem, there is no RL. There's no RL actually. If there is no RL, your V naught is directly 3 volt, no?
But
If-
middle resistor is there.
There is a resistor, but no current will flow if RL is open.
Oh, that's what I'm not understanding.
If RL is there, then is a voltage division.
If it is
See, why
closed,
I'm saying RL is infinite, because the gate problem, you can cross check. No. Yeah.
yes,
Still,
sir. Then on 29th page, sir.
29.
There, how to find Vx?
This one. Yeah. How to find
is it-
Vx?
Yeah.
KCL. V in minus Vx by 1k equal to Vx minus V naught by 2k.
V in equal to V naught by 2. We should substitute that. Then only we'll get Vx, sir.
No. Vx is in the middle of V in and V naught. V naught is 2V in, no?
Yes, sir.
So between V in and 2V in, that means between 1 and 2, that number is 1.33, they are saying. This voltage Vx is going to be 1.33 V in. How to know? You
So
can
can
apply
you write-
KCL like this. See here, you can apply KCL. How to find Vx? Can I apply here? V in
Yes.
minus Vx by 1k equal to
Mm.
Vx minus V naught by 2k. From here, Vx is 1.33 V in.
Yes, sir. Thank you, sir. Thank you, page.
Hello.
Hello, sir.
Hello.
Hello, sir.
Hello.
Hello, sir.
Sir, multiple students are raising their hands. Just rectify this issue.
Yeah, who is this?
Hello.
Ah,
Hello. Sir, can you open bridge rectifier, sir, in the
bridge rectifier. Can you tell me the
starting pages?
yes, starting, right? This is the one.
Yes, sir.
Yeah.
So, sir, can you explain why if minus input voltage, negative input voltage is given, how negative output voltage we get, sir?
V in only, but this V in has got 2 cycles.
Yes, sir.
For a positive cycle, the current will go up. For the negative cycle, the current has to come through. Nature is, for half cycle, it is positive. For the other half, it is negative.
Okay, sir.
Okay.
Sir, yes, sir.
So for positive cycle, it has to travel through D1, R and D3. For the negative cycle, it has to travel through D4, R and D2. Can you see?
No, sir.
No? See here. Which page is that? This one, no? Yeah. See here. It is during positive cycle. During positive cycle, it is traveling like this.
Hello, sir.
Yes, sir.
This is exactly what I have given, no? In the previous case. This is a bridge rectifier, no?
Yes, sir.
Am I right?
Yes, sir. Suppose if it is having negative
yeah.
input voltage and if it is traveling
This is
from
D1,
B to
D2, D3, D4, for example. During positive cycle, how the current will flow? Like this.
yes, sir.
During negative cycle, like this. But in both cases, it is traveling from A to B only.
Suppose if we have
Huh?
if we give the negative input and it is traveling from B to A, then
A to B
will we
only
get
it is traveling. It is not traveling. Negative also you will give, but the current will travel only from A to B. A to B, A to B, A to B, A to B, positive, 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 positive.
no, sir,
If
but
it travels from
B to A, will we get
speak with
positive?
respect to load. Load does not know, resistor does not know whether input is positive or input is negative. Resistor only knows that if current goes from A to B, if it is positive, B to A, it is negative. There is no chance. However, you keep changing the input, the current is always flowing. See, 1 milliampere, 1 milliampere, 1 milliampere, if it flows from A to B, what will be the output? If that is 1K, 1 milliampere peak, 1 volt, 1 volt, 1 volt, 1 volt, positive you will get.
Yes, sir. But I didn't understand, sir. Your voice was breaking at the time. If input is negative and it is passing through B to A, will we get the output as positive, sir? Hello?
I'm having V in. Yeah. See here, I'm having V in.
Yes, sir.
Here there is a load. If the current flows in this direction, current will flow from A to B, no?
Yes, sir.
Current is going in this direction, current will flow from B to A. So what will be the output? First from A to B, then B to A to B, B to A. But
Yes,
in a
sir.
rectifier, what is happening in a rectifier? If you connect diodes like this, A to B. If you connect diodes like this, again A to B.
Okay, sir.
So what will happen now? The output A to B, A to B, A to B, A to B.
So there is no possibility of going from B to A.
Because cleverly we have connected the diode.
Yes, sir.
Are you getting?
Yes, sir. Can you
Yeah.
explain what is a PIV again, sir?
PIV is the max, is just a voltage across a diode. It is just the voltage across a diode. See, can you calculate the voltage across a diode in forward bias if it is ideal? Short circuit, no?
Yes, sir.
So what is the voltage short circuit? 0. Then what is this PIV? It is the peak inverse voltage. Inverse voltage means what?
Hello? 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 Hello?
Hello?
Hello? Sir, your voice got disconnected, sir. Can you explain again?
Hello, can you hear?
Hello?
Hello, sir.
Hello?
Yeah. Can you
Sir?
hear me? I'm saying.
Yes, sir. Yes, sir.
Yeah. So the current direction remains same. Okay.
In the PIV, sir, your voice got disconnected.
I was trying to tell that PIV means you have to
Hello?
Hello, sir.
Hello?
Hello, sir.
Are you getting?
No,
Sir,
sir, your
PIV.
voice.
Yeah. Now,
sir, can you go to 29F, sir?
Sir, your voice got disconnected, sir.
no, PIV is the voltage across a reverse bias diode. I'm saying.
Okay. Sir, in next problem, you have taken the 1K, 1K and 2K, no, sir, on problem. We get 5/3 and 5/2.
Yeah.
Sir, there, why didn't you take it as minus 5/3, sir? You took positive value of VM by...
Because again, A to B current is flowing, no? Rectifier.
I didn't get that, sir.
See the current direction I'm saying. Whether there's a positive cycle or negative cycle, see the current direction. Move your pen. See, a current direction finding is very simple. What you have to do is, you have to take the pen and you have to draw a line. Draw a line from the source and again come back to the same source. See, if you look at the circuit, it's difficult how the current will flow. You have to take the pen and you have to draw the line like this. See here. If you draw the line, you'll understand. You have to take the pen. See here. For this problem, can you see this slide?
Yes, sir. Yes, sir.
This is plus, this is minus. You have to travel from here. You have to take a pen and you have to draw like this. Like this. This is X and this is Y. It's flowing like this. And this one is just coming in parallel. Okay. So similarly for the other case, from minus to plus. From minus to plus. See, for this is minus, this is plus. Current has to flow. You have to take the pen and you have to draw like this. You have to draw. Can you see?
Yes, sir.
From minus to plus. So you have to draw like this. One will go like this. The other one will go like this. Can you see?
Yes, sir. I understood this one, sir. But you have V0 is
No, like
minus
this.
5/3, no, sir.
Like
Next
this.
slide.
V in
V naught is minus 5 by 3, no, sir.
minus 5. What is V in? V in is negative, no? V in, see this, see the cycle here. V in, I am getting some voltage. Please see,
Acha,
V in is
okay.
not a fixed voltage. It is changing
Yes,
from
yes, sir,
0. Let's take some values. 0, minus 1. V in is minus 2. V in is minus 3. V in is minus 5. Can you see those dots?
Yes, sir, yes, sir.
These are the
So
voltages of V in. Okay. Now in this equation, you have to substitute V in equal to minus 1, minus 2, minus 3. Minus of minus will
Minus
become
of minus 5.
plus.
Okay,
Plus.
five.
That is why you're getting plus.
Thank you, sir. Thank
Yeah.
you, sir.
Sir, can you go to
Sir,
20, sir?
Yeah. Tell me, can you go to what?
29F.
29.
Yes, sir.
Yeah.
Sir, for applying the virtual short concept, we need to consider assign the non-inverting terminal voltage to the inverting terminal voltage.
Both are same. Either way you can assign. How VP is VN, VN is VP. It's only same.
Sir, another doubt, sir. Sir, I'll tell one circuit. Can you solve it by Miller effect?
Miller.
Yes, sir.
Yeah. Tell me.
For the op-amp, it is
No,
having.
if circuit, you can send me on WhatsApp. No.
Okay, sir. Sir, for the application of Miller effect, the condition should be that it should have negative feedback and to the inverting terminal, right, sir?
Yeah. If it is given to non-inverting, then you will have negative resistance.
Okay, sir.
If it is
Sir,
given to inverting terminal, you will have positive resistance.
Sir, if op-amp draws no current, but it delivers current, right, sir?
Very good. It has to drive the load. So it has to deliver current.
Sir, in clippers and clampers, sometimes yesterday you solved some problem, sir. Sometimes you are giving AC voltage, sometimes you are giving DC voltage.
Just for problem practice sake, that's all. AC means both positive cycle and negative cycle you have to see.
Okay, sir. Okay, sir. Thank you, sir.
Yeah.
Hello, sir. Can you please go to 11F?
11F. Yeah. Is this the one? Is this the one? Hello? Is my voice audible?
Hello, sir.
Yeah, is my voice audible? I'm saying.
Yes, sir.
Yeah.
So I'm really confused at sketch and the transfer characteristics, sir.
What?
I'm really confused at sketch and the transfer characteristics. Not able to
Which
draw.
transfer characteristic you want me to
Like
draw?
in diodes, totally, sir. In diodes.
That y equal to mx line, huh? You have a problem drawing that
Class, you
line.
can tell me, sir. Today's class 24F.
20?
4F.
Yesterday's class, huh?
No, sir. Today's class.
Acha, today's class 24F. This one?
No, sir. The next
This one?
page. Yeah, yes, sir.
Transfer characteristic. You can take like this. Right? V in and V naught. Now in positive cycle, what are the V in numbers? 0, 1, 2, 3, 4, 5. Can you see the dots?
Yes, sir.
So V in 1, 2, 5. Your V naught is 0, 0, 0. So V in is 1, V naught is 0. V in is 2, V naught is 0. V in is 5, V naught is 0. Can you see the lines?
Yes, sir. I can see.
Yeah. Then V in, V naught. Negative cycle. V in minus 1, V naught is plus 1. V in is minus 2, V naught is plus 2. V in is minus 5, V naught is plus 5. Minus 1, 1. Minus 2.
Excuse me, sir.
Yeah.
Sir. Yeah, I didn't get that V not sketch, sir. V not sketch.
V naught sketch you didn't get.
Yes,
For
sir.
V in less than 0, for all the voltages V in less than 0, V naught is minus V in. No? So
Yes, sir,
what are the
minus
voltages which are less than 0? Tell me. Minus 1.
Minus 1.
Minus of minus 1 plus 1.
Plus 1.
V in is minus 2. Minus of minus 2 plus 2.
Okay.
So when V in is minus,
Hello.
This point, you join them. Are you getting?
Yes, sir. Yes, I got. And then page number. Yes, sir. 31F page number.
31F.
Last question, sir. Last question. Today's last question. Hello. Hello. Am I audible, sir? Hello.
Can you hear me?
Yes, sir. I can hear you.
Yeah, tell me.
Last question, sir. At today's last.
Okay.
I didn't get the diagrams, sir.
Sketch, huh?
Yes, sir. Sketched.
Sure. This one, right?
Yeah.
This one.
Yes, sir.
Yeah. So let conclusion, if V in a
Sir, your voice is disturbing. Hello. So your voice is not clear, sir. Hello.
is greater than -5.
Sir,
All
your
the
voice
upper
is
lines.
not clear, sir.
Yeah, so it's -5 only. Can you see? The all for all
Sir, your
voltages.
voice is not. Sir, your voice is not clear, sir. Can you explain from starting, sir? Hello.
Yeah, can you hear me?
Now I can hear you, sir.
Okay, you can hear me now.
Yes, sir.
Yeah, what I'm trying to say is for V in greater than -5, your V naught is -5.
Yes.
Who is greater than 5?
4, 3.
Lower pole.
Yes.
Your output is going to be -5. So I put a black line here. For this is all for V in greater than -5. Can you see?
Yes, sir.
So this is all for V in.
Hello. Hello. Sir, I'm not able to listen you, sir. Hello.
Is
Hello.
+1. When V in is -9, when V in is -9, your V naught is going to be +3.
Yes.
When V in is -10, your V naught is going to be +5. Can you see? Yes or no?
Yes, sir. Your screen is not visible, sir.
Now?
No, sir.
Okay, wait. Now?
Yes, sir.
Yeah.
Sir, you have told that about gyrator. No, sir. Gyrator.
That is inductor only, no? Just an inductor.
Sir, can you explain me about how to find R naught, sir?
R naught.
Yes, sir.
In where? In general R naught, huh? In which problem you want R naught? So you want to find the output resistance of any amplifier.
Yes, sir. Any amplifier.
Okay.
You have told that
For finding output resistance of any amplifier, you should never consider load. You have to remove load For calculating resistance, you have to short the voltage source first. And at the output, you have to connect some test voltage, VT equal to 1 volt. Find IT. By Ohm's law, R naught is VT by IT or 1 volt by IT. See, simple. I'll give you an example. Suppose I have an amplifier where, can you hear me?
Yes, I can hear you.
Where I connected 1 volt and the current is 0.2 ampere. Then my R naught is going to be 1 by 0.2, which is 5 ohms.
Yes.
Suppose there's some circuit, right? A cascade amplifier, Darlington base, something. I connected 1 volt, my current is 0.2. So resistance is 5 ohms. Before you want to calculate, see that your voltage sources are shorted to 0.
Short.
This is how you calculate the output resistance.
Okay.
Okay?
Okay, sir.
Yeah.
So, non-inverting integrator, sir. I'm really confused that directions, sir. Maybe this is silly question or not.
No question is silly. Everything has its importance. Don't see whatever doubts you have, you can ask me. Don't think this is silly question, that is silly question. Nothing is silly here.
Debo integrator, sir. Debo integrator.
Yeah. Tell me, you have an integrator, you have difficulty in applying KCL?
Yes, sir.
Here there is a capacitor or a resistor here?
Capacitor.
Here there is a resistor, if I remember.
Yes, sir.
Here voltage divider is there.
Yes, sir.
So you do one thing. If you don't want to do in my procedure, here there is V in.
Yes.
So you do one thing, take VP and VN here, no, and do it. Entering
Okay.
current is leaving. Here entering current is leaving, you do. You will get an answer.
Once you find it, no, sir. Once.
What I did was, this is V naught. So if I backtrack, it is V naught by 2 I did.
Yes, sir. V naught by 2.
This is V naught by 2. And now sum of currents that leave a junction is 0 I took. I can take entering equal to leaving also. Either way it is same only, no?
Okay. I got it, sir.
Yeah, good.
And difference between current amplifier, sir. Why it is current amplifier, sir?
Current amplifier mean I naught E should be equal to K times of IN. This is current amplifier. Current amplifier. If your V naught equal to K times of VN, it is voltage amplifier. Are you
So
getting?
in current amplifier, we have whole and current source, no, sir.
Yes.
Why it is a whole and current source, sir?
Why it is current source means even if load changes, current will always remain same. That is a current source.
Yes. Okay.
So I'm changing load, same current. Changing load, current is V by R. Changing RL, I'm changing RL, but my current is always not
Same.
depend on RL, it is always V by R.
Yes.
So I'm changing RL, some current is flowing. 1 milliampere current is flowing. Even if you change RL, 1 milli. So the current is always constant. That is why it's called constant current source.
Okay, sir.
Okay?
Okay, so that's it.
Yeah.
Thank you.
Sir, in last second question.
Last?
Second.
This one? This
In
one?
last second, case 1, sir.
This is case 1. Yeah.
Sir, in this, how did you calculate KCL? Like, there is a VX, not this, sir, last second problem.
This one, huh?
Yes, sir. In this, if there is VX and VX node at the point, how did you skip that VX, sir?
Okay. See, it so happens that suppose I'm having a voltage V. Suppose I'm having 15 volt here. Okay.
Yes, sir.
I'm having 3 resistors. Okay. 1K, 1K, 1K. What is the current I? This ground. This is 15 volt. 15 volt. Now here you will have 10 volt. Here you will have 5 volt. Here this is 0. So what is the current I? You have different options. You can write it is 15 minus 0 by 15 by 3K. 15 minus 0 by 3K. is 5 milliampere. Or you can write 15 minus 5 by 2k. Or you can write 10 minus 0 by 2k. Or this is 15 minus 5 by 2k. Or you can write 10 minus 0 by 2k. Or you can write 5 minus 0 by 1k. Can you see?
Yes, sir.
But the current will always remain same. Yeah.
Okay, sir. Sir, one more doubt is that you said op-amp has a less output resistance.
Yeah, provided the load is connected at the shunt feedback. Feedback we will see later. Output
No, sir,
resistance is generally 0 because the last stage in op-amp is a class B symmetry CC amplifier. Its output resistance is very low.
In that case, sir, it will have high current, no, sir.
No. The output resistance is low means this is an op-amp.
Yes,
Its
sir.
output resistance is low means whatever it generates A times of VD, that will appear across RL. This is the output resistance. It is a voltage, it's a good voltage source, no? So now if this is 3 volt, you will have 3 volt here. Even though you change RL, it is 3. So the output is not dependent on RL because of R0 low. Suppose R0 is having a value equal to RL, what will happen? Half of the signal will go to the load, no? Then
Yes,
what
sir.
is the use of op-amp? 1 plus R2 by R1 we should get. So 1 plus R2 by R1 means even if I change RL, it should be 1 plus R2 by R1. When will it happen if your R0 is much lesser than RL?
Sir, yes, sir, got it. Sir, what is the op-amp, like, does it have any dissipated power?
Obviously, op-amp, it's a device, no? Inside 25 transistors are there. First class, I have drawn a diagram, no?
How to calculate dissipation, sir, in op-amp?
Power dissipation, every node we have to do, every element we have to calculate. That is difficult. Instead, what they do, there are other ways also for calculating. See, why are we doing at input stage, output stage? Because we can skip the whole signal flow. We don't want to go inside. See, why are we modeling it this? Input resistance of first stage, output resistance of last stage, overall gain. These three are enough. It will to cover all the information of those 25 transistors inside. Because input Rin is enough to deal with these two terminals, plus and minus. The output terminal deals with R0 and AVD. Are you getting? That is why this is a very powerful model. This model is enough to calculate the exact op-amp power dissipation or input resistance or currents, everything.
Okay, sir. That's it. Thank you, sir.
Yeah.
Hello, sir.
Yeah.
Open 28.
Hello.
Yeah, tell me.
So for the amplifier, for the op amp, when we have the diode at input side, we can apply anti-log amplifier, no sir?
Yeah. That we will do in the class.
Okay.
Hello, sir.
Okay, sir.
Hello, sir. Hello. Hello. Hello, sir.
Yeah, tell me.
Sir, yesterday notes.
Yeah.
Can you open it?
Tell me what doubt you have.
40F.
40F. Nothing is there.
No.
Oh. Wait. I have to save this. Yeah, tell me. 40F, no?
Sir, here, sir, next page.
This is not the one.
Oh, this. No, that's only 40 only. Yes,
This one?
yes, sir. Sir,
Ah.
sir, here, why are we not taking 5 volts, sir, for V0?
No. There's a drop of 4 volt across 3K. No, there's a drop of 4 volt here. This is 5 volt. This is 1 volt. 5 minus 1, 4 volt is across 3K. 4 by 3K, 1.3 milliamp is flowing.
Okay. In every problem, we are taking the short circuit voltage only. Hello?
Across 3K. What is the current? 4 by 3.
Sir, you are not audible. Before you are not audible, sir. You can
No, I
explain.
was trying to say this is 5 volt, no? Here.
Yes, sir.
It is 5 everywhere till here. It is 1 till here. 5 minus 1 is 4 is dropped across 3K.
5 minus 4 equal to.
5 minus 1 is 4 volt is dropped across 3K. What is the current? 4 by 3 milliamp.
Okay, sir.
Yeah, 4 volt by 3K. 4 by 3 milliamp.
Sir, today, last you told VOP equal to, we have 2 diodes, no, sir, D1 and D2. Hello? 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 Hello, sir? Hello? Hello?
Dear students, I think some technical problems sir is underway. So sir unable will be logged in. So if you have any doubts, you can mail to sir and you can have your doubts. Due to internet problems, sir is went away. So sir will unable to log in. So for today's session is going to be end. And if you have any doubts, you can contact to Kiran sir on mobile. So today I'm ending the sessions.